Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or tutoring, then check out the links in the description below. So now let's get started on our set of questions for today's session. Okay, so question 1. Draw condensed structural formulas for all products obtained from the complete hydrolysis of the following triacylglycerol under acidic conditions. Okay, so this is an example of a triacylglycerol. You see it's a very large molecule. So let's write this down. Okay, so here is the structure that was given in the question. And when we have a hydrolysis of a triglycerol in general, our products are glycerol plus the 3 fatty acids. So we can look at this structure by breaking the bonds kind of at each carboxylic acid group, just so we can visualize the type of products that we will get. So during this hydrolysis reaction, 3 water molecules will react, and like I mentioned earlier, glycerol is one of the products. So to draw glycerol, you can kind of picture it as this whole group right here. Oops. Okay, so I kind of boxed it out so that we can kind of see what its structure looks like. But I will still draw out the product. And you can see it contains all these alcohol groups. So that's how it got its name, glycerol. Okay, so now I'm going to draw all the 3 fatty acids that were obtained if the complete hydrolysis of this triacylglycerol took place. So starting with the top substituent, I'm going to draw the carboxylic acid and then the long alkyl chain. If we count the total number of carbons, we have 14 in the chain plus 2, one from the carboxylic acid group and then the other one from the end methyl group. So since we have 16 in total, this can be written as hexa or 6, deca or 10, so 16, noic acid. So every time we have a carboxylic acid group, we know it will end in ic acid. So I'm going to box this in. And then if we look at our second fatty acid that is formed, let's try to name this one as well. So there is a total of 14 carbons in the chain. So I can name it tetradecanoic acid. And we can put this in a box. And then for our last product, let's draw out the carboxylic acid group first. And we kind of get this long chain that has a double bond in the middle. So the name of this compound is actually oleic acid. Okay, so these are all of the products that are obtained from the complete hydrolysis of this triacylglycerol under acidic conditions. Okay, so the junior tutor said, the hydrolysis of a triacylglycerol produces glycerol and 3 fatty acids. The given triacylglycerol has 2 saturated fatty acids. So their names are actually palmitic acid and myristic acid, and 1 unsaturated fatty acid, oleic acid. The condensed structural formulas of the products from its complete hydrolysis under acidic conditions are as follows. Glycerol, CH2OH, CHOH, CH2OH, yep. Then this is the hexadecanoic acid we drew. Its name is also palmitic acid. So CH3, CH214, COOH, myristic acid, CH3, CH212, COOH. So this is also tetradecanoic acid. And then they have the oleic acid down here. Yep, so this solution is correct. Okay, so now let's move on to question number 2. Acetone, the solvent in nail polish remover, has a density of 0.791 grams per milliliter. What is the volume in milliliters of 20 grams of acetone? Okay, so let's recall the formula that density is equal to mass over volume. So in this case, they gave us the density of acetone, which is 0.791 grams per milliliter. And they gave us the mass, 20.0 grams of acetone. And we're looking for the volume in milliliters. So this question's pretty straightforward. We don't need to do any conversion or anything like that. We just need to rearrange this equation to solve for volume. So volume is then equal to mass divided by density. So now let's sub in 20 grams divided by 0.791 grams per milliliter. And then you'll notice that the grams will cancel out, and our mils are now the main unit. And you should end up getting around 25.3 milliliters. Okay, so the junior tutor said, the density of a substance is equal to its mass over its volume. Thus, the volume is mass over density, 20 divided by 0.791, and they got 25.3 milliliters. This solution is correct. Okay, so question 3 asks, how to calculate the value of the equilibrium constant for the chemical reaction. So let's just write down a general chemical reaction. So the lowercase letters, they represent the coefficients that would be in front of our compounds. And in this case, our elements are the uppercase letters. So capital A is a substance, capital B is a substance that are the reactants, and then the capital C and capital D are products. So Kc is the symbol for the equilibrium constant. And the expression is that starts off with the concentration of substance C to the power of its coefficient, so lowercase c, is multiplied by the concentration of substance D to the power of its coefficient. So these are our products, and this is all divided by our reactants, which is the concentration of substance A to the power of its coefficient, and then the concentration of substance B to the power of its coefficient. Okay, so this is how we would calculate the value of an equilibrium constant for the chemical reaction. So typically the concentrations would be given, and also the reaction would be balanced, and we'll be able to plug the values in to calculate for Kc. So the junior tutor said the equilibrium constant Kc expression can be formed from the balanced chemical reaction. Consider the following reaction. A plus B equals C plus D. AC is equal to concentration of D to the power of its coefficient times the concentration of C to the power of its coefficient divided by the same thing for our reactants. Yep. So this solution is correct. Okay, so on to question 4. Xenon trioxide is reduced to xenon in acidic solution by the iodide ion. Iodide ion is oxidized to iodine, I2. What is the balanced chemical equation of the reaction? So this is an example of a redox reaction. So let's write down what they give us in the question. For our reduction reaction, we have xenon trioxide that gets reduced to xenon. And then for our oxidation reaction, we have the iodide ion, which is I minus, that gets reduced to iodine. Okay, so now I have written down everything that we are given. And the first step is to make sure all the atoms are balanced. So step 1, balance atoms. So starting with the first reduction reaction, you'll notice that there are 3 oxygens in our reactant side, and there are none in the product side. So I'm also going to add that in acidic solution, we add water to add oxygens, and we add H plus to add hydrogens. Okay, so back to our reduction reaction, there are 3 oxygens in our reactant side. So I need to add 3 waters to balance out the oxygens. And after adding water, you can see that there are now 6 hydrogens on our product side. So I need to add 6H plus to our reactant side. Okay, so now those atoms are balanced. In the case of the second line, there are 2 iodines in our products. So I just need to write a coefficient of 2 in front of the iodide ion. Okay, so I'm going to rewrite this down here just so that I have more room to work with. So far we have 6 protons plus the xenon trioxide makes xenon plus 3H2O. So which brings us to step 2, which is to balance the charges. Oh, I didn't even write my oxidation reaction down. Oxidation, 2 iodide ions makes iodine Okay, so step 2, balance the charges. And for this step, we also want to make sure that the number of electrons are the same for both the reduction and oxidation reactions. Okay, so when we balance out the charges, we kind of want the whole we want the charges on our reactant side to be the same as the charges on the product side. So to do that, we need to add electrons to the side that is more positive. So for our reduction reaction, our product side is neutral, since xenon and water are both neutral. But on our reactant side, you can see that there are 6 protons. So I need to add 6 electrons to balance out the positive proton ions. Okay, so similarly, you can see that on our oxidation side, there are 2 negatively charged iodide ions on our reactants. And for our products, there is a neutral iodine. So to balance out these charges, I need to add 2 electrons to our product side in the oxidation reaction. Okay, so like I mentioned earlier, we want to make sure the number of electrons are the same for both the reduction and oxidation reactions. So since there are only 2 electrons for our oxidation reaction, I need to multiply this whole thing by 3 in order to get the same number of electrons that I do have in my reduction side. So multiplying it by 3, we end up getting 6 iodide ions plus 6. Oh, sorry, it is going to be 3 only. Three iodines plus 6 electrons. Okay, so now the electrons are the same for both the reduction and oxidation reactions, and also all the charges are balanced as well. So step 3 is to combine the reduction and oxidation reactions to get overall redox reaction. Okay, so let's combine all of our reactants on one side. So we have 6 electrons plus 6 protons plus the xenon triiodide. And then the reactants for our oxidation is just 6 iodide ions. For all of our product side, we have xenon plus 3 waters plus 3 iodines, and then plus 6 electrons. Okay, so now we just want to cancel out the electrons from both sides since they are the same. And then let's also double check that everything is balanced. We have 6 hydrogens on both sides, 1 xenon, 3 oxygens, and 3 iodines. And for our charges, we have 6 positive charges balanced out with 6 negative charges. And for our products, everything is neutral. So the net balanced, let's just rewrite it. Okay, so now let's see what the junior tutor said. Balancing a redox reaction is different from balancing a simple chemical equation. In a redox reaction, you need to balance each half reaction, reduction, and oxidation. The number of electrons in each reaction should have the same amount, and in order to balance the charge in the product and reactant side, H+ can be added. Lastly, to balance the number of hydrogen on each side, water can be added. So as you can see for mine, we have different approaches. I like to balance my atoms first because it's easier to balance the charges after that. But to each his own, whatever you get comfortable with doing. So they showed how they added their electrons on this side. And they added 2 on this side. Yeah, again, like it makes more sense for me to balance the oxygens first. Just so that it's kind of like easier, you know how many protons you want to add. And then I like to balance the charges. But the junior tutor still ended up getting the same answer. Xenon trioxide plus 6 H plus 6 iodide ions make xenon plus 3 iodines plus 3 water. So this solution is correct. Okay, so for question 5, it asks, draw an electron dot structure for the cyanide ion Cn-. In aqueous solution, this ion interacts with H+ to form the acid. Should the acid be written as HCN or CNH? Okay, so for Cn-, let's first find out the total valence electrons. So for carbon, there are 4 valence electrons, and for nitrogen, there are 5. And we also have a negative charge, so we need to add an extra electron. So this gives us 10 electrons in total to work with. So first, let's write carbon single bonded to the nitrogen. So each bond contains 2 electrons. So if I had 2 here, I just need to draw 8 in the form of lone pairs. So let's say I did 1, 2, 3, 4, 5, 6, 7, 8. You kind of get this structure here, but you can see that nitrogen does not have a full octet. So I'm first going to bring one of the pairs of electrons down to form a double bond. So again, nitrogen doesn't have a full octet. So I'm going to bring another pair down, and we are going to form a triple bond. Okay, so now both carbon and nitrogen have a full octet, and I showed that there was a negative charge. So this is the Lewis diagram, but the question asks for electron dot structure. So to draw that, it's pretty much going to be the same thing, except instead of the bonds, I'll show how these electrons form a triple bond. And you kind of get this as our electron dot structure. Okay, so for the last part of the question, they ask, should the acid be written as HCN or CNH? So our H plus will react with the carbon atom. So therefore, it is written as HCN. Okay, so let's see what the junior tutor said. The electron dot structure of cyanide is as follows. Yep, so that's what I got as well. The carbon atom and the nitrogen atom of cyanide are connected by a triple bond. Note that in this case, the carbon atom is more likely to be the carrier of the added electron, because by having a triple bond, the nitrogen atom is able to satisfy the octet rule, hence making it less susceptible for reactions with other molecules. This is why in aqueous solutions, the H plus ions will interact with the carbon atom, hence the acid should be written as HCN. So this solution is correct. Okay, so question 6. What is the net ionic equation of the reaction of magnesium sulfate with strontium nitrate? Okay, so step 1 is just to write down the double displacement reaction that occurs. And make sure that all of the atoms are balanced. So we have magnesium sulfate plus strontium nitrate. So these are both aqueous. And for these types of reactions, it's important to write the phase that it's in. Okay, so if we were to draw this as a double displacement reaction, we have the magnesium that bonds now with the nitrate. And we have the strontium that bonds with the sulfate. Okay, so notice that I didn't write the phases yet for our products because we need to look at the solubility rules to find out whether or not these compounds will separate into their ions or if they will precipitate in the solution. Okay, so these are the solubility rules. All compounds of group 1A, lithium, sodium, potassium, and ammonium are soluble. all common nitrates are soluble, and acetates and perchlorates. So for our reaction, we have magnesium nitrate. So this is a common nitrate. So this will be soluble. So I'm going to write it as aqueous. And then continuing on, all common chlorides, bromides, iodides are soluble. All common sulfates are soluble, with the exception of calcium, strontium, barium, silver, and lead. So notice that we have strontium 2+. So now this confirms that this will precipitate in solution and not be soluble. So its phase is in the solid phase. Okay, so after we balanced this double displacement reaction and we figured out all of the phases that they have, step 2 is to separate them into ions. So all of the species that are in the aqueous phase will be separated into ions. So we have magnesium 2+, plus SO4 2-, plus strontium 2+, plus 2NO3-. So those are all of our reactants. All the products are Mg2+, 2NO3-. And then for the strontium sulfate, this is the only one that doesn't separate into its ions since it remains a solid. So it's just going to be strontium sulfate solid. So step 3 is to remove the spectator ions. So these will appear the same in both our reactant side and our product side. So in our case, we have magnesium 2+ that appears on both sides, and we also have 2 nitrate ions that appear on both sides as well. So finally, we can write down our net ionic equation. And we end up getting SO4 2- plus strontium 2+ makes the solid strontium sulfate. Okay, so now let's see what our junior tutor said. The net ionic equation for the reaction of magnesium sulfate with strontium nitrate is SO4 2- plus strontium 2+ makes strontium sulfate. Explanation. The net ionic equation is a chemical equation for a reaction that lists only those species participating in the reaction. Net ionic equation is commonly used in acid-base neutralization reactions, double displacement, and redox reactions. There are 3 main steps. 1, write the balanced chemical equation, and then 2, write the equation in terms of all the ions in the solution known as the total ionic equation. Break all of the strong electrolytes into ions. They form an aqueous solution. And make sure to indicate the formula and charge of each ion. Use coefficients to indicate the quantity, and write aqueous after each to indicate it's an aqueous solution. In the net ionic equation, all species with solid, liquid, and gas will be unchanged. Any aqueous that remain on both sides can be cancelled out. These are called spectator ions. Spectator ions are ions that remain unchanged on both sides of a chemical reaction and does not affect the equilibrium. Knowledge and solubility rules of compounds is a large advantage. The solubility rules determine the compounds that break into ions in aqueous solution. Okay, so these are all the solubility rules that I looked up in this table here. So the more you do like solubility reactions, the more you kind of get used to how to use the solubility chart. So I'm just going to skip all the rules and get to solving the problem. Step 1, write the balanced chemical equation. And then they determined the nature of the compounds on the product side. So they saw that the nitrates are soluble and most sulfates are insoluble, meaning strontium sulfide is in solid state. Write the total ionic equation for the reaction. So this is separating them into the ions. Step 3, cancel out all the spectator ions present in the total ionic equation. This will leave us with the net ionic equation. Yep, so the solution is correct. Okay, so question 7. What do you do in acid-base titration laboratory experiments? Okay, so when we have an acid-base titration, the goal is to determine the concentration of an acid or a base. And to do that, we neutralize that solution, neutralizing it with a standard solution of acid or base. So these standard solutions have a known concentration. So depending on if you're trying to determine the concentration of an acid, that means we neutralize it with a standard solution of base. And on the other hand, if we try to determine the concentration of a base, that means we neutralize it with a standard solution of an acid. Okay, so when we perform acid-base titrations, we slowly add the standard solution to our unknown. And we know when to stop by using a pH indicator. Let's try to draw out the reaction. So let's say we had an unknown concentration of acid in our flask. In this burette, we have a volume of base. And before we start adding the standard solution of base, we want to take note of the volume that we started at. So this is called initial volume. Okay, so once we take note of the initial volume, we can start adding the base dropwise into our unknown acidic solution. So, like I mentioned earlier, a pH indicator is used to monitor the progress. So typically the acid will be colorless, but we can add a pH indicator such as like phenolphthalein, which turns pink once the solution is neutralized and when it turns more basic. So when we get like a light pink solution, then we know that we can stop the reaction. So we can stop adding more base. And then we want to end up finding out the final volume of base in the burette. So we know exactly how much base was added to the acid in order for it to be neutralized. And then from there, we can calculate the concentration of our unknown by using concentration is equal to number of moles over volume. Okay, so let's see what the junior tutor said. Titration is a technique to determine the concentration of an unknown solution. In any titration experiments, there are several parts of the titration setup. The titrant, a solution of known concentration, which is added to another solution whose concentration has to be determined. So the analyte is the solution whose concentration has to be determined. These substances will react, and the reaction is an acid-base reaction, which results in salts and water. During titration experiments, the use of indicators is essential because this will tell you the end point of the titration experiment. Indicators are substances that change in color in response to chemical change caused by changes in concentration in hydrogen and hydronium ions in the solution, simply change in pH. So we can also have indicators that depended on the potential of the solution, but that's a different story altogether. Like, they don't change in color. Once they get to a certain potential, then that's how we know how to stop the titration. But anyways, the common materials and equipment to be used in any titration experiments are the acid, base, indicator, burette, clamp and stand, beakers, flask, safety goggles. Okay, so here they have their diagram, much better than mine. They have the burette clamp and the stand, and then they show our analyte, which has unknown concentration in the flask, and the known concentration in the burette. Step 1, set up the equipment. 2, fill the burette with known concentration of acid or base. 3, take a burette reading from the top of the meniscus. So this is the initial reading. 4, place a flask with unknown concentration of acid and base. 5, add the appropriate number of drops of indicator. So it's usually like 1 or 2 drops. 6. Slowly add the titrant to the flask while constantly stirring gently in a circular motion. 7. Keep adding the titrant until a visible color change happens. The lighter the color change, the better. Step 8. Take the final reading of the burette. 9. Calculate the pH of the titrant. So this solution is correct. Okay, so question 8. What is the name of the chemical formula HiO3? Okay, so let's look at all the options. Periodo acid, hypoiodic acid, iodic acid, iodate acid. So this is actually iodic acid. And let's see what the junior tutor said. Acids are named based on the anion that is attached to the hydrogen. In our example, the anion of the acid is iodate. Okay, so let me show how this can be written. Into its ions. So this is the iodate ion. We remove the ate suffix and replace it with ic. Then we add acid to the end of the name. So for this acid, its name is iodic acid, which is C. So this solution is correct. Question 9. What is the oxidation number of chlorine? So when chlorine is in its gaseous state, so when it's a gas, it is Cl2. The oxidation number is 0. I'll also add that when chlorine is bonded to another atom, it typically has an oxidation number equal to -1. So for example, if we had hydrochloric acid, the hydrogen has a +1 oxidation number, chlorine is -1. Let's also look at like sodium chloride. The sodium has a +1 and the chlorine has a -1. So it pretty much just depends what state it's in. Okay, so the junior tutor said the oxidation number or oxidation state of chlorine depends on the compound that chlorine is found in. If chlorine is in its gaseous state, Cl2, oxidation state of chlorine is 0. If chlorine is found in any other compound, the oxidation state varies. To get the oxidation state, we must recall the rules for assigning oxidation state. These rules are shown below. Oxidation state of an atom in an element is 0. Oxidation state of a monoatomic ion is the same as its charged. So like if we had just chlorine on its own that has a negative charge, then its oxidation number is -1. In covalent compounds, the oxidation state of hydrogen is +1. Oxygen is assigned an oxidation state of -2, except in peroxides where its oxidation state is -1. In binary compounds, the more electronegative element is assigned a negative oxidation state equal to its charge in its ionic compound. And lastly, the sum of the oxidation states must equal the charge of the compound. So if we had a neutral compound, like HCl, then the sum of the oxidation states of the hydrogen and the chlorine must equal 0. So that's why +1 and -1 gives us a neutral compound. Okay, so this solution is correct. And I think we have time for one more question. Question 10, what are spontaneous reactions? So spontaneous reactions, they favors the formation of products at the conditions under which the reaction is occurring. Okay, so if we know the delta G, which is the Gibbs free energy of the reaction, if we see that it's negative, so when delta G is less than 0, then this tells us the reaction is spontaneous. So as an example, ice melting in warm water is a spontaneous reaction. So it pretty much takes place without us having to add any extra energy to it or anything like that. Yep. So let's see what the junior tutor said. A spontaneous reaction is a reaction that occurs under a given set of conditions. If a reaction is spontaneous in one direction, it cannot be spontaneous in the opposite direction. There are several ways to measure the spontaneity of a reaction. One of them is to measure the change in the Gibbs free energy. Reactions in a constant temperature system will be spontaneous in the forward direction if delta G is negative. If delta G is positive, the forward reaction is not spontaneous, but the opposite direction is. When delta G is 0, the reaction is in equilibrium, and there is no net change in the reaction. So this answer is correct. I'm also going to add what I said as well, just so that we're clear. All right. So those are all the questions for today's session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you'd like this video, go ahead and give it a thumbs up and a comment. And don't forget to share with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.